Your smart home is watching you. It's also watching your electricity meter spin faster than it should. The average connected home wastes 23% of its energy budget on phantom loads, standby power, and poor scheduling. Most cloud based energy monitoring systems are busy phoning home with your consumption patterns instead of actually reducing your bills. Smart home energy management done right means local control, protocol aware automation, and zero reliance on third party servers that treat your power usage as monetizable data. I rebuilt my entire energy monitoring setup after discovering my so called smart thermostat was uploading granular temperature and occupancy data every 90 seconds. The alternative isn't giving up automation, it's building a system that works for you, not against you. So, what is smart home energy management? Smart home energy management is the use of connected devices, sensors, and automation logic to monitor, control, and optimize electricity consumption across your home. Unlike passive monitoring, where you just check a dashboard occasionally, true energy management involves automated responses, cutting power to idle devices, shifting high consumption loads to off peak hours, and dynamically adjusting HVAC based on occupancy and time of use rates. The core components work across three layers. First is monitoring. This means real-time power measurement at the circuit level, device level, or whole home level using CT clamps or integrated metering chips. Devices like the Emporia View Gen 3 energy monitor use Zigbee for local communication, avoiding cloud dependencies for core functionality. If you're curious, check the link below to see the current price. Second is control. Smart plugs, relays, and switches can cut power or throttle loads based on automation rules. Protocol matters here. Z-Wave, Zigbee, Thread, and Matter all handle switching commands differently, with latency ranging from 50 milliseconds for Thread mesh to 800 milliseconds for Wi-Fi bridges under congestion. Third is automation logic. These are if-then rules executed locally on a hub like Home Assistant, Hubitat, or a Matter controller that trigger actions based on thresholds, schedules, or external conditions like electricity pricing signals. The key distinction here: cloud-based systems like Sense and Neurio, along with many Wi-Fi smart plugs, upload your consumption data continuously, often selling aggregated insights to utilities or researchers. Local-first systems using Zigbee or Z-Wave energy monitors paired with Home Assistant keep data on your network and execute automations without internet access. Your energy patterns reveal when you're home, when you sleep, and what appliances you use. That's data worth protecting. Now let's talk about how smart home energy management actually works. Smart home energy management operates through a closed feedback loop. Measure, analyze, decide, act, repeat. Here's how each protocol and device type fits into that cycle. Starting with the measurement layer, energy monitoring happens at three granularities. Whole home monitors measure total consumption at the breaker panel using CT clamps around the main service lines. The Sense energy monitor samples at 1 megahertz to detect device signatures, but requires cloud processing for disaggregation. It won't identify devices offline. The Emporia View Gen 3, by contrast, offers local API access via Zigbee and can push raw power data to Home Assistant without cloud routing. Accuracy varies. You get about plus or minus 2% for resistive loads like heaters and incandescent bulbs, plus or minus 5 to 8% for inductive motors like refrigerators and HVAC compressors, and plus or minus 10 to 15% for switching power supplies in electronics. CT clamp placement matters. If the clamp isn't perpendicular to the wire or is too loose, readings drift. Circuit-level monitors track individual breakers. This is useful for isolating high-consumption circuits like HVAC, water heater, or EV charger. The Emporia View supports up to 16 circuits via expansion modules, each with 50 milliamp resolution. This granularity lets you build automations like notifying yourself if your heat pump is struggling based on power draw and outdoor temperature. Device-level monitors embed power metering into smart plugs or relays. Zigbee plugs like the Sonoff S31 or Third Reality report wattage every 5 to 10 seconds with plus or minus 1 to 2% accuracy on resistive loads. Z-Wave plugs like the AOTech Smart Switch 7 support instant power reporting but add 200 to 400 milliseconds of latency versus Zigbee due to security handshaking. Thread and Matter devices, available since late 2024, promise sub-100 millisecond latency for power reporting. But as of early 2026, Matter 1.4's energy cluster implementation is inconsistent. Some vendors report cumulative kilowatt hours only, others add instantaneous watts, and a few include voltage and current metrics. Verify the specific attributes supported before assuming full metering capability. Moving on to the control layer, switching protocols and response times. Once you know what's consuming power, you need to control it. Here's where protocol choice directly impacts automation reliability. Zigbee operates on 2.4 GHz with 250 kilobits per second data rate. Mesh topology means each powered device acts as a router, extending range. Latency for on-off commands averages 80 to 150 milliseconds in a healthy mesh with 6 or more routers, degrading to 300 to 500 milliseconds with weak signal paths. Zigbee plugs require a coordinator like a CON-B2, SkyConnect, or Hub integrated radios. Z-Wave uses sub-gigahertz frequencies for better wall penetration but lower data rates at 100 kilobits per second. The mesh supports up to 232 nodes with 4-hop maximum. Command latency runs 150 to 400 milliseconds with S0 security and 200 to 600 milliseconds with S2 encryption enabled. Z-Wave Plus version 2 with 700 series chips improved range by roughly 50% over older hardware. It requires a Z-Wave controller like an AOTech Z-Stick or built-in hub radios. Thread and Matter layer IPv6 routing over the radio, allowing direct IP addressing to devices. Border routers like HomePod Mini, Google Nest Hub 2 Gen, or Eero 6 routers bridge thread mesh to your LAN. Latency runs 50 to 120 milliseconds for local commands when the controller supports native thread. Matter 1.4 compatibility doesn't guarantee local operation. Some Matter-certified plugs still route commands through cloud bridges despite protocol support. Test before deploying. Wi-Fi smart plugs from brands like TP-Link Casa and Shelly have 300 to 1,200 milliseconds depending on router congestion, DHCP lease times, and whether the firmware requires cloud validation before executing local commands. Many Wi-Fi plugs ship with firmware that blocks LAN control unless you also accept cloud access. Read the EULA. Shelly devices are an exception. They're fully functional via local HTTP API with no cloud requirement. Fallback behavior matters for energy automation. If your hub crashes or loses power, Zigbee and Z-Wave devices retain their last state but stop responding to new commands until the coordinator restarts. Thread and Matter devices can reroute through any available border router if multiple exist, maintaining control even if one fails. Wi-Fi devices with cloud dependencies may freeze in their last state or default to on, which is dangerous for heaters or dehumidifiers. Now let's discuss automation logic and local execution. Effective energy automation lives on your hub, not someone else's server. Here are 3 common patterns. First, peak hour load shedding for time of use rate optimization. If the current time is during peak hours and your grid power exceeds a threshold, automatically turn off devices like pool pumps and dehumidifiers and set the thermostat to eco mode. Most utilities publish time of use schedules as JSON or CSV. Scrape and cache locally. Don't rely on cloud APIs that fail or change endpoints. I pull PG&E rates weekly via curl, parse into Home Assistant's template sensors, and trigger automations without external dependencies. Second, phantom load elimination. If your TV standby power is below 3 watts and there's been no activity for 30 minutes, turn off the entertainment center. Measure standby draws first. My living room entertainment center pulls 47 watts idle with the soundbar on standby, receiver's clock running, and streaming box sleeping. A Zigbee relay cuts that to 0 when no motion is detected for 30 minutes. Annual savings? Roughly 411 kilowatt hours, about $65 at my rates. Third, dynamic load balancing to prevent tripping breakers on shared circuits. If your garage circuit power plus EV charger power exceeds the circuit limit, automatically reduce the charger's current. Then increase it again when the garage power drops below 1,000 watts. This requires circuit-level monitoring and a charger with adjustable current limits like ChargePoint HomeFlex or JuiceBox Pro. It prevents nuisance breaker trips when you run a table saw while the EV charges. Before deploying any device, you should audit its network traffic. I run all new gear on an isolated VLAN with firewall logging for 72 hours. Here's what I found. Sense Energy Monitor made 2,847 HTTPS requests per day to Sense.com, Amazon AWS.com, and Segment.io. Uploads include per-second waveform data, even when not viewing the app, device signatures, and location coordinates. It cannot function offline and blocks local API access entirely. Emporia View Gen 3 made 143 requests per day to Emporia.com when cloud integration was enabled, but local Zigbee control works completely offline after initial setup. You can block internet access after configuration and retain full monitoring plus automation via Home Assistant's local Emporia integration. TP-Link Casa plugs with firmware version 1.0.8 or later require cloud authentication every 6 to 12 hours, even for LAN commands. Older units with firmware below 1.0.5 work indefinitely offline via local API. Ship firmware carefully. Downgrading requires UART access and is not reversible via the app. Shelly Plug S Gen 2 had 0 cloud requests when configured in local-only mode. MQTT and HTTP endpoints respond with less than 20 millisecond latency. Best cloud-free viability in the Wi-Fi category. For protocols, Zigbee and Z-Wave devices inherently operate locally since they have no IP stack to phone home, but hubs or bridges may upload aggregated data. Thread and Matter devices can operate locally, but many first-gen implementations route through cloud controllers anyway. Verify before buying. So why does smart home energy management matter? You're not installing energy monitoring to make your utility company happy. You're doing it because automated load control cuts bills by 15 to 30% without manual intervention, prevents infrastructure overload like that garage circuit problem I mentioned, and if done locally, keeps your consumption patterns private. The financial case is straightforward. The average U.S. household uses 10,500 kilowatt hours per year at 16 cents per kilowatt hour average. That's $1,680 annually. A 20% reduction via smart scheduling, phantom load cuts, and HVAC optimization saves $336 per year. Hardware investment for a local first setup runs $400 to $600, yielding payback in 18 to 24 months. After that, pure savings with no subscription phase eating into returns. Time of use optimization magnifies this in markets with extreme rate differentials. PG&E's ETOU/C plan in California charges 53 cents per kilowatt hour peak from 4 to 9 p.m. versus 32 cents per kilowatt hour off-peak. Shifting 4 kilowatt hours daily from dishwasher, laundry, and EV charging from peak to off-peak saves $307 per year on that load alone. Reliability matters more than you think. Cloud-dependent systems fail when your internet goes down and automation stops entirely. When the vendor shuts down or pivots like Revolve, Lowe's Iris, and Insteon did, when API rate limits trigger during high usage, or when firmware updates break integrations. Google broke Nest API access twice in 2025, killing third-party automations for weeks. Local execution means your heating doesn't stop optimizing because Amazon servers hiccuped. I've run my Home Assistant energy setup through 3 internet outages, ranging from 6 hours to 4 days during wildfire evacuations, with 0 automation failures. Everything continued: phantom load cuts, HVAC scheduling, even solar diversion to the water heater via ESP home relays monitoring my inverter's Modbus stream. Privacy is the third pillar. Granular energy data reveals intimate details: when you wake, when you cook, when you're away for extended periods, even what you watch. 4K streaming has distinct power signatures versus 1080p or idle. Insurance companies already buy this data from automakers. Progressive settled a lawsuit over Tesla data resale in 2025. Utilities want it for demand response programs, but often share with third-party analytics firms. Build your system locally, and that data never leaves your walls. Let's look at the types of smart home energy management systems. Smart home energy management architectures fall into 3 categories based on where intelligence lives and how much cloud dependency you tolerate. First are cloud-dependent centralized systems. These route all data and automation logic through vendor servers. Examples include Sense, Nereo, and most Wi-Fi smart plugs with app-only control. The pros are easy setup, slick mobile apps, and often ML-based device disaggregation that identifies what's running by analyzing current waveforms. The cons are total dependence on vendor stability, mandatory data upload, subscriptions creeping in, no functionality during internet outages, and potential for cloud-side processing delays. I've seen 2 to 5 second lags between tapping off in the Casa app and the plug actually switching. Cloud-free viability score, 0 out of 10. If the internet dies, so does your automation. Next are hybrid local cloud systems. Data is measured and stored locally, but cloud services handle advanced analytics or remote access. Examples include Emporia View with Home Assistant integration, Shelly devices with optional cloud sync, and Habitat with cloud backup. The pros are that core functionality survives internet loss. You control retention and processing, and you get optional cloud features for remote monitoring when traveling without forcing dependence. The cons are that it requires technical setup like installing Home Assistant, configuring MQTT, and managing certificates for remote access. Vendor updates can still break local APIs, though this is rare. Initial configuration often requires cloud authentication before local access unlocks. Cloud-free viability score, 7 out of 10. Works fully offline after setup, but you'll need to block firmware auto updates and verify each update doesn't re-enable cloud dependencies. Third are fully local systems. All measurement, storage, automation logic, and control happen on your LAN. Examples include Zigbee or Z-Wave plugs paired with CON-B or Z-Stick in Home Assistant, ESP Home-based DIY monitors, and Shelly devices in local-only mode. The pros are maximum privacy, zero vendor lock-in, indefinite functionality regardless of internet or cloud service status, sub-second automation latency with no round trip to distant servers, and no subscriptions ever. The cons are a steeper learning curve since you're the sysadmin, limited mobile app polish, no ML device disaggregation, though ESP Home plus custom models are possible for the dedicated, and it requires local network security hardening with firewall rules, VLAN segmentation, and certificate management. Cloud-free viability score, 10 out of 10. My system runs on a Home Assistant Yellow with local Zigbee and Thread radios, 14 Zigbee energy monitoring plugs, one Emporia View with the Zigbee coordinator blocked from internet after setup, and ESP Home nodes reading Modbus data from my solar inverter. It's operated flawlessly through 3 ISP outages and 2 voluntary air gap periods when testing attack surfaces. Let me mention some protocol-specific considerations. Matter 1.4 energy management is still maturing. The spec includes energy measurement clusters for instantaneous power, cumulative kilowatt hours, voltage, and current, but implementation varies wildly. Eve Energy Thread Plug reports full metrics, while some early Amazon Smart Plug Matter Edition units only expose on-off control with no energy data. Check before buying. Matter certified doesn't mean all clusters implemented. Zigbee's CZL metering cluster is well established. Most Zigbee plugs report instantaneous demand in watts, current summation delivered in kilowatt-hours cumulative, and voltage and current on newer devices. Reporting intervals are configurable from 1 second to 3,600 seconds, but frequent polling drains battery sensors. For powered plugs, set to 5 to 10 seconds for responsive dashboards without mesh congestion. Z-Wave's Meter Command class supports multi-channel metering and historical data retrieval. Some devices cache the last 24 hours locally. The downside is that reports are polled, not pushed, so you configure intervals in your hub, increasing traffic, versus Zigbee's attribute reporting, where the device decides when to send updates based on value changes. Now, let's walk through building a cloud-free energy management system step by step. I've iterated through 4 different energy setups since 2020. Here's the architecture that actually works without compromise. For your hardware foundation, you'll need a hub or controller. The Home Assistant Yellow has Zigbee and Thread radios integrated, with local-only processing on Raspberry Pi CM4. If you're curious, check the link below to see the current price. An alternative is Hubitat Elevation C8-8 with Z-Wave 800 and Zigbee 3.0 if you prefer appliance-like setup over flexibility. For whole home monitoring, use Emporia View Gen 3 with 8-circuit expansion. Install CT clamps at the panel. 2 on the mains, since 240-volt split phase requires 2 CTs, and 6 on high-consumption circuits like HVAC, water heater, EV charger, dryer, range, and office. Connect to a Zigbee coordinator. Do not connect to Wi-Fi during setup or it'll push you into cloud configuration. Use Home Assistant's Emporia integration in local Zigbee mode instead. For device-level control, get about 12 Sonoff S31 Zigbee plugs for controllable loads, like entertainment center, dehumidifiers, space heaters, pool pump, workshop tools, and server rack. These report power every 5 seconds with plus or minus 1.5% accuracy and cost around $12 each, far better value than Z-Wave equivalents. For HDAC control, use Ecobee 3 Lite with Home Assistant local API integration with no cloud polling. The official API requires cloud, but the unofficial Ecobee local custom component talks directly to the thermostat over LAN using reverse-engineered endpoints. Alternatively, flash a generic Zigbee thermostat or use ESP Home to build a custom controller interfacing with your existing HVAC control wiring. For optional solar integration, set up an ESP Home node with ESP32 and RS485 transceiver reading Modbus registers from your solar inverter. This provides real-time production data for diversion logic, sending excess solar to water heater instead of exporting to grid at unfavorable rates. Total hardware runs about $650 for complete local monitoring plus control. Let me give you some automation examples with actual logic. For time-of-use-aware load scheduling, you can shift your pool pump to off-peak hours. Set a trigger at 9 p.m. when off-peak starts, add a condition checking if the pool pump ran today, then turn on the pool pump, wait 4 hours, and turn it off. This avoids the 53-cent per kilowatt-hour peak window entirely, cutting pool pump costs from $187 per year to $116 per year by shifting 4 kilowatt-hours per day from peak to off-peak at 32 cents per kilowatt-hour over 7 months of operation. For solar diversion, you can heat water with excess production. When you're exporting more than 2 kilowatts to the grid for a sustained 5 minutes and your water heater temperature is below 130 degrees so you don't overheat, turn on the water heater relay for 1 hour, then turn it off. Instead of exporting solar at 8 cents per kilowatt hour, you're using it to heat water that would otherwise cost 32 cents per kilowatt hour to heat during evening hours. Net savings, 24 cents per kilowatt hour on 2 kilowatt hours daily equals $175 per year. For adaptive HVAC based on occupancy and outdoor temperature, when the home has been unoccupied for 30 minutes, set the thermostat to 60 degrees if outdoor temperature is below 32 to keep pipes from freezing, or 55 degrees for a deeper setback when it's mild. Combined with return to comfort triggers 30 minutes before typical arrival times learned via presence detection patterns, this cuts heating by roughly 18% versus fixed schedules that assume regular 9 to 5 occupancy. Let me also mention privacy-first alternatives to cloud energy monitors. If you already own cloud-dependent hardware, here are local replacements that do the same job without the data leakage. Instead of Sense, use Emporia View Gen 3 Local Zigbee plus Home Assistant. You lose ML device disaggregation, but gain privacy and reliability. If you need disaggregation, run your own NILM models locally using Flare, an open-source project for device signature learning on Home Assistant. Instead of Nest thermostat, use Ecobee with local API or a Zigbee thermostat like the Zen 01 paired with remote sensors. Nest requires cloud even for basic scheduling, which is unacceptable for local control. Instead of CASA smart plugs, use Shelly Plug S in Wi-Fi with local-only mode, or any Zigbee energy monitoring plug like Sonoff S31, Third Reality, or Akara. Z-Wave options include AOTech Smart Switch 7 if you're already invested in that protocol. Instead of Wemo Insight, use literally anything else. Wemo devices have a notorious history of firmware breaking local control, requiring cloud authentication, and randomly losing connection. I tested a Wemo Insight switch for 14 days in 2024. It dropped offline 6 times, requiring power cycle plus cloud reauthentication each time. Avoid. Now, let's talk about common pitfalls and how to avoid them. I've burned through over $800 in failed hardware and broken integrations learning what doesn't work. Here's what to watch for. First pitfall: protocol mismatches kill reliability. The problem is mixing Wi-Fi, Zigbee, Z-Wave, and Thread devices without understanding mesh limitations creates dead zones and dropped commands. For example, I installed 6 Zigbee plugs around my house, 3 upstairs and 3 downstairs, assuming the mesh would self-heal. It didn't. The plugs formed 2 separate clusters with no bridge between floors because my metal HVAC ductwork blocked 2.4 gigahertz propagation. Commands to upstairs devices timed out 40% of the time. The solution is to map your environment before deploying. Use a Zigbee sniffer or the neighbor table feature in Home Assistant's ZHA integration to visualize mesh topology. Place at least one powered router device within 30 feet of every endpoint. For Z-Wave, run a network heal after adding devices to rebuild routing tables. Metal structures, aquariums, since water absorbs 2.4 gigahertz, and microwave ovens all degrade mesh performance. Thread's ESP6 routing theoretically handles this better, but as of early 2026, Thread mesh stability degrades rapidly beyond 20 devices in homes with complex layouts. Matter 1.4's multi-fabric support, connecting devices to multiple border routers simultaneously, helps, but firmware support is inconsistent. Second pitfall, cloud dependencies sneak back in. The problem is devices advertised as local control still require cloud authentication for initial setup, firmware updates, or optional features that turn out to be required for automation triggers. For example, Lutron Caseta advertises local control via its Smart Bridge Pro. True, but only for basic, on-off. If you want occupancy sensing from their motion sensors or time of use scheduling, you must enable Smart Away mode, which uploads location data to Lutron servers continuously. There's no way to access the raw sensor data locally without cloud activation. The solution is to search before buying. Look for device name plus local API or device name plus offline mode on forums like Home Assistant Community, Reddit's Home Assistant, or Habitat forums. Look for integration methods that explicitly avoid cloud, like ESP Home custom firmware for many Tuya Smart Life devices, MQTT bridges like Zigbee to MQTT or ZHA for Zigbee, and Z-Wave.js to MQTT for Z-Wave, or local polling like Shelly's HTTP endpoints. Avoid anything requiring a phone app for initial setup if the app demands account creation. That's a red flag. The device won't function offline. Third pitfall, over-engineering automation logic. The problem is complex multi-condition automations with nested if-then-else logic break when a single sensor fails, causing the entire rule to freeze or behave unpredictably. For example, I built an automation that adjusted my office AC based on occupancy from a PIR sensor, desk power draw from a smart plug monitoring my computer, outdoor temperature from a weather API, and time of use rate tier from a utility screeper. It worked beautifully until the weather API went offline during a storm. The automation threw errors and stopped executing because the template couldn't resolve the outdoor temperature state. The solution is to design for graceful degradation. Use default values in templates that fall back to reasonable numbers if a sensor is unavailable. Keep high-value automations simple, with 1 to 2 triggers and minimal conditions. Break complex logic into smaller automations that can fail independently without cascading. I now run 3 separate office climate automations. One for occupancy-based setback with just PIR and climate control. One for time-of-use rate-based temperature offset with just rate tier and climate adjustment. And one for outdoor temperature limits with just weather and min-max overrides. If one breaks, the others continue working. Fourth pitfall, underestimating phantom loads. The problem is assuming off devices consume negligible power. Many don't. For example, my TV entertainment center pulled 47 watts idle. Soundbar, 8 watts, AV receiver, 12 watts, cable box, 14 watts, Roku, 3 watts, HDMI switch, 2 watts, USB chargers, 8 watts. Over a year, that's 411 kilowatt hours wasted, $66 at my rates. The solution is to measure everything before optimizing. Use device-level energy monitoring plugs to audit standby draws across your home for 2 to 3 weeks. you'll find surprises. Laser printers use 5 to 15 watts idle for the heat fuser element in standby. Game consoles use 8 to 18 watts when off in instant on mode for downloads. Desktop computers use 4 to 12 watts powered down with Wake Online or USB charging enabled. Garage door openers use 3 to 7 watts continuously for LED standby and radio receiver active. Cut anything over 2 watts that doesn't need 24/7 availability. I use Zigbee plugs with occupancy timeouts for entertainment center, office printer, and workshop tools, and saved $112 per year on phantom loads alone. Let's move on to some advanced techniques. Once basic scheduling and phantom load cuts are working, you can optimize further with real-time grid data and predictive logic. For time-of-use optimization with dynamic pricing, some utilities like PG&E, SDG&E, and ComEd offer real-time pricing where rates fluctuate hourly based on grid demand. You can automate around this if you cache rate data locally. I scrape PG&E's Oasis API every 15 minutes, parse the JSON, and store rate tiers as Home Assistant sensors. Automation shifts loads when rates dip. For example, charge your EV when the current rate drops below 25 cents per kilowatt hour, as long as the EV battery level is below 80%. This requires a smart EV charger with local control, like ChargePoint HomeFlex via local API, or Wallbox Pulsar Plus with MQTT bridge, plus rate data cached locally. Never pull external APIs from automation triggers. Latency breaks logic. Savings potential? On days when real-time rates swing from 15 cents per kilowatt hour overnight to 80 cents per kilowatt hour during heat waves, shifting a 50 kilowatt hour weekly EV charge saves $32.50 per week during extreme events. Annual average, assuming 12 extreme swing weeks, roughly $390. For load balancing across shared circuits, if you have high consumption devices on the same circuit like EV charger plus power tools or kitchen outlets plus microwave plus electric kettle, prevent breaker trips with dynamic current limiting. Monitor your garage circuit power continuously, then adjust the EV charger's current limit based on available circuit capacity. Calculate the circuit maximum, subtract current load and a safety margin, then set the charger to use what's left, capped at the charger's maximum rating. This requires circuit-level power monitoring from Emporia View or Sense with individual CT clamps, plus a charger with adjustable current limits via local API. I run this on my garage circuit shared between EV charger, workshop tools, and garage door opener, and haven't tripped the 15-amp breaker once in 18 months, even when running a table saw while charging. For solar diversion and battery integration, if you have rooftop solar and export generation to the grid, diverting excess to heat water or charge batteries locally often beats selling at low net metering rates. My setup includes a SolarEdge inverter with ESP Home reading Modbus registers for real-time production in watts, a 50-gallon electric water heater with contactor relay controlled by Zigbee switch, and grid export monitored via Emporia View CTs on mains. The logic triggers when you're exporting more than 2 kilowatts for a sustained 5 minutes during peak solar hours from 9 a.m. to 4 p.m., and the water heater temperature is below 135 degrees, so you don't overheat. Turn on the water heater contactor for 1 hour, then turn it off. Annual savings? Roughly 2 kilowatt hours per day diverted from export at 0.08 kilowatt hour to offset evening grid consumption at 0.32 kilowatt hour. Net gain? 0.24 kilowatt hour times 2 kilowatt hour per day times 280 sunny days equals $134 per year. For battery systems like Tesla Powerwall or Enphase Encharge, similar logic applies. Charge during cheap or solar hours, discharge during peak pricing or grid outages. Most battery systems offer local Modbus or RESTful APIs. Avoid Tesla's cloud-only control if possible. Use Powerwall 2's local gateway instead. Now let's address some frequently asked questions. Can smart home energy management work completely offline without cloud services? Yes, a fully local system using Zigbee or Z-Wave energy monitoring devices paired with Home Assistant or Habitat operates indefinitely without internet access. After initial configuration, which may require temporary cloud authentication for some devices like Emporia View, block internet access at the firewall, and all core functionality continues locally. Power monitoring, automation execution, device control. The trade-off is losing cloud-based conveniences like ML device disaggregation from Sense's signature detection and remote access when away from home, unless you configure your own VPN or reverse proxy tunnel. I've run my setup through multi-day internet outages with zero automation failures because all logic executes on the local hub, not remote servers. Which smart home protocol is most reliable for energy monitoring and control? Zigbee offers the best balance of latency, device cost, and ecosystem maturity for energy monitoring as of 2026. Zigbee energy monitoring plugs typically respond to commands in 80 to 150 milliseconds on healthy meshes, cost $12 to $25 each, and integrate seamlessly with Home Assistant, Habitat, and most open-source coordinators. Z-Wave provides better wall penetration with sub-gigahertz frequency versus 2.4 gigahertz, and slightly more robust security with S2 encryption standard, but costs 2 to 3 times more per device and adds 200 to 400 milliseconds latency due to encryption overhead. Thread and Matter 1.4 promise sub-100 millisecond latency and native IP addressing. But as of early 2026, Matter's energy cluster implementation varies wildly by manufacturer. Some devices report full power metrics, others only expose on-off control despite Matter certification. Verify specific attribute support before committing to Matter energy devices. How much can smart home energy automation realistically reduce my electricity bill? Households implementing comprehensive energy automation, phantom load elimination, time of use scheduling, HVAC occupancy-based setbacks, and solar diversion where applicable typically achieve 15 to 30% reductions in total electricity costs. For the average U.S. household using 10,500 kilowatt hours annually at 16 cents per kilowatt hour, roughly $1,680 per year, a 20% reduction saves $336 annually. Higher savings occur in regions with extreme time-of-use rate differentials. California's PG&E charges up to 53 cents per kilowatt-hour, peak, versus 32 cents per kilowatt-hour, off-peak, making load shifting dramatically more valuable. Initial hardware investment for a local-first system runs $400 to $600, yielding payback in 18 to 24 months. After that, savings compound indefinitely, with no subscription fees ever eating into returns, unlike cloud.